Welcome to Polymers 3. This is the third lecture on polymers. First, I'm going to start by going over the objectives of today's lecture, and I move on from where we stopped last time. We've already covered fundamentals of polymer science and technology. We also discussed thermoplastic polymers in details, and we also talked about thermosetting polymers, and we also discussed those. Today I'm going to talk about elastomers, and I'm going to talk about polymer recycling and biodegradability. These are very important topics that I'm going to discuss today. So let's get started. I'm going to talk about elastomers. Elastomers are the type of polymers that are capable of large deformation. This deformation is elastic, and this deformation is as a cause of relatively low stresses. And anyone who experienced with elastomers, they know that sometimes they could really get extended and stretched. Some can be extended 500% or more and still return to their original shape. It is because of this characteristics of elastomers that they are used in many applications, including the packaging industry. It would be nice to have such a material to be able to behave elastically while still preserve its characteristics. There are two main categories of elastomers: natural rubber and synthetic polymers. Natural rubber, they're derived from biological plants, mostly rubber and other trees that their juice could be extracted. By juice, I don't mean to compare it with orange juice, but the juice of the trunk of the tree, and they extract that, and they made natural rubber out of that. And this goes back to centuries ago. However, synthetic polymers are more advanced, and they are it's much newer than the natural rubber. Synthetic polymers are produced by polymerization processes like those that we previously talked about before, TP and TS polymers. How does the molecules of elastomers they look like? These are long chain molecules, and they are cross-linked. Remember that the other type of polymers that was also cross-linked was the thermosetting polymers, or TPs. And there are two features that are associated with this behavior of elastomers, with this type of elastic properties. Molecules are tightly kinked when they're on a stretch, and the degree of cross-linking is less than thermosets by many accounts. That's a really a substantial amount. An example of the molecules are shown down here in the unstretched form. It's exhibited A down here to your bottom left hand side of the screen. When we stretch them or apply a stress sigma to it, as shown by two arrows on exhibit B down here, and these molecules, the chain-like molecules, they really get stretched and they become to the form that you see down here. And when it is released, these molecules, because they are cross-linking or cross-linked, they go back to its original shape. Of course, beyond some level of stress, they're going to break. One should not forget about that. But it's this unique shape of the molecules of elastomers that provide them with such a desirable characteristics for many applications. Okay. So what happens as we stretch them? Let's take a look at that in a more systematic way. When we stretch them at the beginning, we force the molecules to pretty much get straightened out, like the previous figure that I just showed you, part B, going from part A to part B. And then, of course, there will be some resistance because molecules, they don't want to get untangled or uncoiled and straightened. So that's where you see that initial resistance. When you have a piece of rubber in your hand and when you pull two sides away from each other, you'll see that it's not really easy to do, and that initial resistance is as a result of the forces that do exist between the molecules and resist the untanglement as a result of the force. As we are pulling this more, we get over that initial resistance. There will be also more forces, and that stiffness becomes more stiff, because from that point on, now we try to break that covalent bonds of those cross-linked molecules that we discussed previously, and then that would come into play, and the resistance or the stiffness would actually increase. And of course, when we are making elastomers, if you have more cross-linking, and this would be more difficult, the elastomer would become more stiff, and the modulus of elasticity is more linear. Again, that's a desirable property in many cases. Let's take a look at the stress strain diagram for rubber. I've shown this for different types of material, except for ceramics, because for them behavior doesn't exhibit much strain, and it's pretty brittle. So there are three types of rubbers that are shown here. One is the hard rubber. It's that line that's more straight, and it exhibits less strain and more stress. The second line in the middle is the vulcanized or soft rubber. And the last one down here is the crude or natural rubber. As you can see, with the crude or natural rubber, the strain is much higher. Of course, this is for a sample with the same cross-sectional area that we put under testing. We don't compare apples to oranges in engineering, or we shouldn't. Here, a good example of comparing apples with apples and oranges with oranges. So the cross-sectional area of these material that are shown here on the stress strain, they're all the same. They went under the same type of force, and this is the behavior, and they're drawn on the same diagram. So as you can see, with a crude natural rubber, the strain is much higher, but if you want to continue with the stress, it's going to be somewhere down here. The vertical axis is an increasing axis. It starts from 0 down here, and as we are adding to the stress, it goes up along the y-axis. The strain also the same way. It is to the right positive. It's 0 to the right. So as you're going to the right of strain curve, the strain would be high. In the case of vulcanized rubber or soft rubber, again, the stress is higher, but as you can see, strain would be lower. And as we are moving away to hard rubber, you can see that the stress is much higher, and the strain for a particular point, which could be a point on this diagram, we continue this, and the strain would be lower. What does this tell us? This tells us that as rubber, as the type of rubber becomes more stiff, or as we move toward the type of the rubber that becomes pretty stiff and strong, as we increase the stiffness, we would actually reduce the strain. So in this case, hard rubber can take a much higher stress level, but it can break easily, as you can see, in comparison to other types of rubber. So beyond the point in which it cannot anymore strain, that means that's the point that it actually breaks, or it start have those micro cracks, and rupture would occur beyond that point. So this curve should give you a good idea as to how different types of rubber would actually behave, from hard rubber to vulcanized or soft rubber, or to crude or natural rubber. What is vulcanization? I've been using this term probably throughout the discussions on polymers. This is a term for curing in the context of natural rubber. When we say curing, we are talking about cross linkage, and of course the cross linkage in rubber is 1 to 10 links per 100 carbon atoms in the linear polymer chain. This is depending on the degree of desired stiffness. In the case of natural rubber, what's abbreviated here as NR, it's a high molecule weight polymer, C5H8. Again, it derives from a latex type, like a milky type of a substance produced by various plants. Most of them, the one that's shown down here, is a picture of a rubber plantation. These are rubber trees, and we don't even leave the trees alone, and we actually extract rubber from them. Isn't that great, or what? So looking at these different types, we see that we have first the milky substance, or the natural rubber. From there we get the latex. It's a 1/3 water by it's actually 2/3 water by weight. There are also other ingredients involved. Then from latex we move on to rubber. You've probably seen that some products doesn't contain latex because some people are allergic to latex. So some industries are moving away from using latex, but that's also another important material when we talk about natural rubber. So what are some of the properties of vulcanized natural rubber? They have a high tensile strength, and they have, of course, as a result of that, that means that they are resistive to tear, and they have a high tear strength, and that is for the elastic range, and they can recover to the original shape very quickly, and as a result they are good for wear and fatigue. Of course, in their own league, we're not going to compare them in this category with anything of steel, aluminum, or other types of material. We need to look at it among rubbers. Remember, comparing apples with apples and oranges with oranges. So what are some of the drawbacks of natural rubber? Well, they don't do well when they're subjected to heat, sunlight, oxygen, ozone, and oil. And we can play with some of these weaknesses or drawbacks by adding additives, and that will reduce some of these less desirable characteristics. About 22% of total rubber by volume is actually natural rubber. Some products, the best example or the largest single market for NR is automotive tires that we all use for our cars. There are also other products, seals, some of the shock absorbing components. I bet you didn't know about that. Also noteworthy is something that's probably not as common as it should be, and that is many of these big chunks of rubber. They're basically chunks of rubber, but they're polymers, and they are used in larger buildings, in areas of high seismic activities, and we actually put the buildings on those rubbers before those rubbers get connected to the ground. They change the frequency of shaking and make the building pretty shake resistant or earthquake resistance. Those are not common areas. In tires, an important additive to natural rubber would be carbon black. The carbon black would actually reinforces the rubber. It is going to increase tensile strength, and it is going to increase the resistance to tear and abrasion of the tires. Other additives are clay, silica, and calcium carbonate, and other chemicals that accelerate and promote vulcanization. Let's move on to synthetic rubbers. Synthetic rubbers are man-made, and actually it was as a result of world wars. Every time you have a war, a major war, then a material becomes scarce. The transportation of the material would be disrupted. The black market would be pretty much established and all that. So wars are not a good thing. But as a result of world wars, mankind always think about creative ways to address some of the challenges. And one thing that was developed as a result of world wars, it was the development of synthetic rubbers. It was pretty motivated, largely motivated by when the natural rubber was difficult to obtain. So currently, if you want to look at the weight of how much synthetic rubber is used versus NR natural rubber, synthetic rubbers is now more than three times of natural rubber. There are different applications, different molecules. The copolymer butadiene, it's C4H6, and styrene CH. C8H8, and they are styrene butadiene rubber, or SBR is another. These are three important synthetic rubbers that are used in the industry. And the main raw material for synthetic rubbers is petroleum. Byproduct of that is used to make synthetic rubbers. What's a thermoplastic elastomer? Thermoplastic elastomer, they behave like an elastomer, and they have certain properties that are important to discuss. The elastomeric properties are not actually from the cross links that we have discussed, but it is more from the physical connection between soft and hard phases in the material. These material, they cannot, of course, match the conventional elastomers when we increase the temperature and in creep resistance. Creep also another thing that it's important in material, and we always look at that as well, make sure the material is creep resistance. Some products of the thermoplastic elastomers are footwears. Many of the shoes that you've seen around, part of it or all of it, usually a good part of it. Rubber bands, extruded tubing, wire coating, molded automotive part, but not any tires. Let me talk a little bit about plastics recycling, because that's a very important topic when we talk about when we discuss materials and processes. One must note that we always have to think about what's going to happen when the material that we use, they're either not in use anymore, or they get discarded, or simply when they are replaced by another material. What do we do with what's left, and also with the waste? And plastics recycling is an important issue to address. It's not an easily discussed topic. Some people, they have very strong feelings about polymers and their recycling. But my intention here is not to cite data or references in which, in my opinion, they're biased. So I'm going to stick with our engineering discussion and try to stay as biased as possible and present the facts to you here. Approximately 200 million tons of plastic products are made every year throughout the world. That's 200 with 60 tons. Okay, so it's 200 million tons. In America, we use about roughly somewhere between 20 to 20, some statistics, 20 to 30 million tons of plastics. That's a lot of plastics. The problem that we're having is, the problem with recycling of these is that many times these plastics, they don't, they're combined with other materials. It is very difficult to separate them. It is costly to separate them. And when there's no market for the end product, of course, nobody is going to invest money on it unless we come up with more technologies, newer technologies that currently we have, and to be able to make that profitable. Only about 6% of the U.S. tonnage is recycled as plastic waste. Think about that number is really not much. 25 million tons times 0.06, and that'd be the end, right? 1% of 25 million would be 0.25. 6 times 0.25, about 1 point some million, and that's about it. The rest either stays in the product because it's could be a part of the product, which is not very difficult, which is not easy to separate, and more difficult to separate, and we let it stay there, or it may end up in a landfill somewhere, a garbage landfill. So the problem that we are having here is, of course, when we do recycling, we try to recover the material, the discarded, in this case, plastic items and corresponding items, and we try to make them into new products. That's why when some of these products are pretty much combined with other products, that could be a very difficult thing to do. Again, recap some of the problems in plastic recycling. Economics of metal recyclings are more favorable because the items are usually larger. Economics of glass recycling are more favorable because glass products are all based on silicon dioxide. This is a nice way of actually putting some of the problems in plastic recycling. Plastic products are generally small. They are made of a variety of chemical compositions. They do not mix well. It's labor intensive. It's just difficult, more difficult, and more not very economically feasible to do those. Now, the industry has come up with something that make the recycling of plastics more easier, and that is the plastics identification code. On every plastic product, there is this plastic identification code. It's a symbol, as you can see there, 3 arrows of it's like a triangle, and there's a number in between. Next time you see a plastic product, try to read and compare it with this little chart that I give you here. There are different, actually 7 of them. First one is PET. It's the polyethylene, and the next one is the high density polyethylene, HDPE. And the third one is PVC, and the fourth one is low density polyethylene, LDPE, PP, PS, and there are others. Number 1 is PETE, number 2 is HDPE, number 3 is V or PVC, number 4 is LDPE, PP, PS, and others. So V and PVC, they are used interchangeably. And these numbers, they tell us what a plastic resin is, and as I mentioned, they would help out with the recycling of the plastics. So all of the plastics covered by the plastics identification number, plastic identification code, PIC, are thermoplastic polymers. It helps out, but as I mentioned, sorting different types of plastic is a very labor-intensive activity. It's really not very cost efficient. So recycling of thermosets and elastomers is more difficult because of the cross-linkage that I just mentioned. Now think about in the case of tires and other types of polymers, it's really not something that we can just say, hey, we're going to melt it and we're going to pretty much cast it again. It just doesn't work like that because it's going to lose many of its wonderful and attractive properties. So what is a biodegradable polymers? They are not conventional plastics because the conventional plastics are not biodegradable. And these are plastics that decompose due to the actions of microorganisms in nature, meaning that if we throw them somewhere in the landfill, the decomposition process takes place due to the presence of all the microorganisms in nature. There are two main forms of biodegradable plastics. One is the partially biodegradable, that's number one on the list, and the second one is the completely biodegradable. And the partially biodegradable one, as the name implies, part of it would be degrade, one of them will not going to be biodegradable, not subject to that. And the completely biodegradable, they are made of kinds of polymers plus filler in which they are biodegradable. So as far as the recycling is concerned, of course, we are after developing products that are completely biodegradable. So we are biodegradable plastics are highly desirable. Both the polymer and filler, they are pretty much derived from natural and renewable resources. If we can develop them from corn, wheat, rice, potatoes, if you can get those cellulose from flax or hemp and use them as fillers, and the polymers that I just mentioned, the starch, then that'd be very helpful. Now this brings me to the end of the slides for polymers. If you have any questions, comments, something would like to discuss, please feel free to send them to me via the course website. I hope you find these topics very useful to help you with your study. Thank you.